What's up, scholars? We're going to do some notes here on Unit 4, Work, Energy, and Power. So as we discussed, work is a force applied in the direction of displacement times that displacement. So you can see here I've got a force directed at an angle, let's call it angle theta, acting on a mass. And what we can do is break that into vector components. So you've got the perpendicular force to the direction of motion, so it's moving horizontally. There's part of that force is directed upwards, and then there's the parallel force, the one that's actually directed in the direction of displacement. So the simple way to write, so work is force parallel times d for displacement, or you can use delta x or whatever you'd like. And then if you do the trigonometry, I'll just skip to what it ends up being. F parallel ends up being f cos theta. So we're getting here, very importantly, the horizontal component. It's not always the horizontal component, but instead it's always the one in the direction of motion. So we can rewrite this, instead of f parallel, write f cos theta. And then instead of writing f cos theta d, we just tend to group the f and d together and then throw the cosine theta out front. So the cosine theta is there to make sure we're pushing or pulling in the direction that we're moving. So we're going to primarily be using that definition, and oftentimes, for example, if you're just pushing in the direction you're moving, then the theta will be 0. So we're going to do an example, but before we do that, I want to make sure that we're comfortable with the units for when we talk about work. So let's break this down just a little bit more, and then we'll be able to more clearly see what the unit will be for work. So force, as we've very completely discussed, force is mass times acceleration. So F equals ma, and that's just going to be times d. And then, honestly, for our purposes, let's assume it's in the direction. Theta doesn't have any relevant units. So anyway, we're here. We've got work is, and then we'll put this in brackets. This is normally how we notate that we're doing the units. So mass is measured in kilograms. Acceleration is meters per second squared. And then, of course, the displacement is going to be measured in meters again. So we're going to get kind of a weird unit. It doesn't really have a lot of intuitive sense from my perspective, but maybe you folks can understand why. But anyway, it comes out to kilograms meters squared per second squared. What is one of those? Well, we call that a joule. If you've taken chemistry, you're probably familiar with that as a unit. So if we have 1 kilogram being accelerated at, well, being moved or had work done on it, meters squared per second squared, that equals exactly 1 joule. Written out, 1 joule is written like this. It's some French guy's name. Alright, so let's use what we know about the equation and the units for joules, or for work, pardon me. And let's see if we can answer a question from our book. So this one says, a shopper pushes a grocery cart 20.0 meters at a constant speed on level ground against 35.0 newtons of frictional force. He pushes in a direction 25 degrees below the horizontal. What is the work done on the cart by friction? What is the work done on the cart by the gravitational force? What is the work done on the cart by the shopper? Find the force the shopper exerts using energy considerations, and then what is the total work done on the cart. So I'm going to draw the picture or I'm going to screenshot that so you can see that on the page, and we're going to work through it. Alright, so here's my lovely sketch of a person pushing down at an angle of 25 degrees with unknown force. We do know that the frictional force acting against the cart is 35, that should be capital newtons, and we're pushing for 20 meters. We have a bunch of things we're trying to find here. For A, we're trying to find the work done by the force of friction, and we're going to end up using this equation here. We're going to end up simplifying it, but let's plop that down here. So the work done by friction is going to be the frictional force, let's call that FF, times the distance that the friction acts over, times cos theta. Now, it's going to be really helpful in this case, and in pretty much every case, because we're still talking about forces sort of indirectly. When we're talking about specific work questions, we should probably get ourselves a nice free body diagram. Let's do it for the cart. So we'll start with easy. The cart, we know it has a weight of mg. We know that there's going to be some frictional force pushing horizontally. So that's going to be this one here. Let's call that FA in the x direction. And then similarly, we're going to have another force directed downwards on the cart. That's going to be the y direction of that frictional force. In fact, let's actually draw that arrow so that we can see. So in the problem, it's mentioned that we're down by an angle of 25 degrees. I'll just put that in there. And so here is that FAX I just wrote out, FAX. And then there's going to be a similar force, FAY. Let's see if we can get it focused here. A little bit, maybe. So we have FAY acting downwards. So we can add that, and I'll add it in black to be consistent. So there's another force, and that's FAX acting down. I'm sorry, in the y direction, acting downward. And then of course we're going to have a normal force that's going to be equal and opposite to both of those forces combined. So we need to draw it a little bit longer than the weight force. It's going to be our normal. And then of course we've got the frictional force going backwards. Now we're told it's moving at constant speed, so let's make our frictional force the same. So FF should be the same, and I didn't draw very well, but the same length as the applied force. In other words, we're moving at a constant speed. There's no acceleration. In fact, this entire situation has zero acceleration. So now that we've got our free body diagram, we can be equipped to solve this whole thing in what I think is a pretty straightforward way. So let's start with the first one. We want to know the work done by friction. So the work done by friction is going to just be the frictional force times how far it was pushed. We know those things already. Times cos of the angle. And this is where it takes a little bit of interpretation, but in fact, if you look at our free body diagram, you can see that it's just straight up in the x direction, and we kind of defined that to be 0. So here we're going to say that theta is equal to 0 degrees, and to be clear, that's for friction only. Okay, so what I mean by that is this force is still pushed at 0. Here we're talking about specifically the angle of the frictional force. So let's plug in all the information. Scholars, so I wrote in what the frictional force and what the distance and what the cos of the angle is, except right before I punch this in, I realized that we forgot about something. Forces are a vector. So very important, this frictional force is directed backwards. And this is another important concept. This work is going to be negative work. Negative work means that energy is being removed from the person shopping cart system and it's being transferred to the floor and to the wheels in terms of friction. So what I need to do is pop a negative in there, and then when I got 700, I'll just pop the negative out front. So my work done by friction is negative 700. It's going to be times cos theta. I did this in kind of a funny way. If you're in pre-calculus, you know cos of theta is just 1. So that's going to come up a lot, and I'm actually going to, it looks like I'm going to cross it out, but I'm going to make this 1. So when we multiply by 1, we still just get negative 700, and then our unit, remember, is joules. So I'll just pop a J on there, and we are done. So the net work done by friction is negative 700 joules, and I'm just going to add this for context. That means that we removed 700 joules of energy. All right, so we've made quick work of A. Let's look at B. It says, what is the work done on the cart by the gravitational force? So that one seems kind of weird. So it says, what's the work done by the gravitational force? Some of you have been writing that FG. I've been choosing to write it as the weight force. They mean the same thing. Remember, to get work, we have to have force and displacement. Something can't just be, like you're not actually doing any work in a mechanical sense like we're talking here if you're just pushing something and it's not moving. So in a sense, gravity is pushing this cart down and nothing's happening. It's not accelerating or moving any displacement whatsoever. So you actually can jump straight to the answer, but let me show you mathematically why this works. If we do F d cos theta, okay, the force can be literally whatever you want. It could be as big as a car, but because the displacement in the y direction is 0, that means that this whole term is 0. 0 joules of work are done by the gravitational, because no work was done because there was no displacement. So You can be justified in an AP exam or questions for homework, etc. In a question like this, what's the work done on an object that's not moving? You don't even need to show the math. You could just say work is 0 joules because no movement. Specifically, no displacement. So part C says, what is the work done on the cart by the shopper? Now, we're going to come to very shortly another way you could answer this question in a little bit more of a conceptual way. But what we can do is we can just look straight here at our equation. So we can say the work done by the shopper on the cart is going to be the force times the displacement times cos theta. And we can kind of cheat here. We know this force, and we actually already know this angle in kind of a sneaky way. Remember, only forces that are directed in the direction of motion count when we're talking about work. So this applied force in the x direction is the same as the frictional force, but in the opposite direction. And we know that this is the only force that matters. The force that they exerted down into the ground, we actually don't really care about. So this force is this force. The frictional force was negative 35. This applied force in the x direction, the actual direction, in the actual direction of movement is 35. So the work done by the shopper on the cart, which I'm just calling WC, is the force positive 35 newtons times the displacement of 20 meters, and then again cos of 0 degrees. So it's actually exactly the same calculation as before. And we're going to talk about this, but that means that no net work was done on this. The friction pulled out 700 joules of energy. The person added, they applied 700 joules of work, which translates into energy. And so in the end, and you can connect these dots here, but that means that no net work was done. And we're going to talk more about this later, but just to preview this, you could have known that because this thing's kinetic energy wasn't changing. We weren't adding energy to the system or taking it away. The amount of energy that was in the system was staying constant, at least in terms of the mechanical energy. Anyway, we'll talk a lot more about that later on. Let's jump into letter D. I love this question, D. We just came off our unit on forces, so there's actually a pretty easy way to answer this question to do with forces. And by easy, I'll just slide it onto the screen there. Here's how you'd find this hypotenuse. You'd just use some trig and then the Pythagorean theorem without doing the details because we're going to do it with energy. You get something like 38.5 or something like that. I think I rounded. So anyway, that was just a really quick back of the envelope calculation. Let's look at it with energy considered. Okay, so we've got our equation. We are looking to find force. What do we know? Well, we know the work done on the cart by the shopper. That's just 700 joules. We know the distance is 20, and we know that the angle was 25 degrees, now that we know the actual force that we exerted in the beginning. This force here, which I already showed you how you could get it with forces. We're going to do it here using energy, or work in this case. Really, the words work and energy are going to become interchangeable. So let's solve for F. That's the force the shopper exerts at that angle we discussed. So if I divide both sides by d cos theta, you get a cancel here. We end up with d cos theta. So the work done by the shopper on the cart is 700 joules divided by d cos theta, plugging all of that in. We get 700 joules divide by 20.0 meters times cos of 25 degrees. And I'll save you the hassle of a calculator. You end up with 38.6 newtons. This time we didn't round, but these are the same answer, right? We got the same answer, one using forces and one using this work equation. So, last question, what is the net work done on this cart? Which, again, we'll talk later, is going to mean how much energy is added or lost from the system. But here we can see that I think pretty easily. The amount of positive work added to the system is 700 joules. This was positive work done on the cart. Now, we actually got ahead of ourselves here. I already jumped to the fact that no net work was done, and we can see that. The positive work that was added by the shopper, 700 joules, the negative work removed by, or the energy removed by the friction in the floor and in the wheels. So what we end up with is the work done on the cart by the shopper plus the work done by friction. We plug in those numbers, 700 joules plus negative 700 joules removed by friction, and again, not surprisingly, we have work net is equal to exactly 0 joules. So scholars, that was quite a lot in that problem. We addressed many, many different things. So refer back to this when you look at some of your future questions just like this in your homework. Thanks so much.